Assalamu alaikum. Dear students, I welcome you to the first lecture of Probability and Stochastic Processes. My name is Dr. Muhammad Akmal Bhatt and I'll be your instructor for this course. This is a graduate level course and I hope that you will enjoy learning very interesting things that we'll be covering in this course. Since it's a graduate level course, the contents will be presented at a level much higher than an introductory undergraduate level probability course. So there are few prerequisites that you must meet to fully benefit from this course. You must have an eagerness to learn new things, and secondly, you must have a strong background in mathematics, particularly set theory and differential calculus. You should have a clear idea of differentiation and integration of function of one variable and functions of more than one variable. Particularly, you should have a clear understanding that for a function of one variable, the integration is area under a given curve, and for a function of two variables, the integration is the volume of the surface above the xy plane or the other axis that we will be dealing with. The first question that we must ask is that why we need to study probability theory. Dear students, we live in an unpredictable world. Things around us change, and they change not according to our expectations but according to the effects of factors and forces that are affecting those things. As long as we are alive, we are part of this dynamic world. We interact with things around us that change as the time goes by. Many times we are the cause of the change, but most of the time we are at the receiving end and we make decisions based on what we see around us that is happening. For example, weather change. Things move from one place to other. We move from one place to other, from one place like our home to the other place like our place of job or our university. Sometimes we move from one city to another or even from one country to the other. So we are moving, things are changing around us, and they change in such a complicated manner that we cannot predict precisely what is going to happen in future. So we need to study probability theory because we live in an unpredictable world, and most of the time we have a complete lack of knowledge about the things around us. Even if we have some partial knowledge of the factors that are affecting the things around us, we cannot precisely measure the forces that are affecting the things around us. And then these forces that are causes of the things that are happening around us, the cause-effect relationship, the model describing the effect of a certain input to a certain output that we observe is quite complicated. It is sometimes so complicated that we cannot precisely calculate the effect of the forces that are affecting the things around us. Hence, we cannot predict precisely what is going to happen in future. It will be clear with some examples. Let's take example of traffic accidents. We can say that we cannot predict if an accident is going to happen or not. For example, suppose a bus is going at a very high speed from one city to another, and unfortunately, unexpectedly, the tie rod or some other component which is part of the steering mechanism of the bus fails. It breaks down. The driver loses control of the bus. He loses his ability to steer the bus, and bus either hits a tree or some vehicle coming from the oncoming traffic. We can argue that such an unfortunate incident cannot be predicted, but if we carefully monitor the components of the bus, particularly the critical components of steering mechanism, and if we replace those components from time to time, maybe, perhaps maybe, such an unfortunate incident can be avoided. It's true that failure of a mechanical or electronic component cannot be precisely predicted because it is aging and it can fail at any time, but a proper maintenance schedule and a careful observation of the quality of components can be effectively used to reduce the possibility of such unfortunate incidents. Let's take another example, an artificial example perhaps. Suppose you want to cross a road. You want to go to the other side of the road and you decide to not look to your right or left and just start moving on the road. It's quite possible that if you blindly start moving on the road, you may get hit by a vehicle or you may not. It depends upon the traffic condition on the road that you are going to cross. The point is, without any knowledge of the traffic situation, if you venture on the road, then it's an unpredictable event. You have a total lack of knowledge about the traffic condition and you may or may not get hit by a vehicle. Let's take example of partial knowledge. Suppose that you look just on one side and start crossing the road. Many people do that. Actually, we are told as we are children that one should look at right side and left side before crossing the road. But if you just use the partial information of the traffic condition on one side of the road, then again it is unpredictable that you will get hit by a vehicle or not. So what you should do, you should have as much knowledge, you should gather as much knowledge as possible before interacting with your surroundings. So suppose you are careful before crossing the road, you look to your right, look to your left, and you see some vehicle coming. What you should do? This is a dynamic environment. Vehicle is moving. You can see clearly with your visual observation that vehicle is moving and it's coming towards you. You need to find out how many seconds you have before the vehicle is going to reach here. How can you find this time? For that, you have to know what is the distance between you and the vehicle that you are watching, and what is the speed with which the vehicle is coming towards you. With just visual observation, you cannot precisely measure these two effects. Maybe the vehicle is 35 meters away, but your guess could be 32 meters or 37 meters. So your measurements are not precise. Human visual measurements for measuring the distance between 2 points or measuring the speed of a moving object cannot be precise. If you had a radar gun, perhaps you can measure the distance and the speed of the approaching vehicle very accurately, but in this case you don't need that. Based on your experience, if you feel that vehicle is 30 meters or more away and it is not moving at 100 kilometers per hour, it's coming slowly at a speed of 20-30 kilometers per hour, then you know that you have a few seconds and you can safely venture out. So we live in an unpredictable world, but being inquisitive animals, we try to gather information about this world and make decisions, intelligent decisions that benefit us. While we are talking about roads and unpredictable accidents that happen on road, let's talk about a social issue. It is well-known fact, we have complete knowledge of this fact, that it is very dangerous to ride a motorcycle at very high speed without wearing a helmet and by lifting the front wheel up in the air. But many young people of our nation disregard this knowledge and they do these kind of things, and we hear about them on newspapers on 15th of August every year. Similarly, it's well-known fact that it is very dangerous to ride a motorcycle with a small child sitting on the petrol tank, particularly in February. when there is a lot of kite flying going on, and stray kites and its strings can easily cut the throat of the young child. We have this knowledge, and we sometimes, unfortunately, disregard this knowledge, and many accidents happen. So people try to have knowledge about their surroundings so that they can deal with unpredictable world in an intelligent manner, but sometimes they have the knowledge but make decisions which are going to affect them in a non-beneficial manner. So once again, we live in an unpredictable world. We try to gather knowledge about the things around us and make intelligent decisions. But sometimes we cannot gather complete information about our surroundings, or sometimes the forces which are affecting the things around us are changing those things in such a complicated manner that we cannot precisely predict the outcome of an event. Now that we are talking about the dynamic world and gathering of knowledge, the humans are being inquisitive animals, inclined to gather knowledge about the things around them, and then disregarding this knowledge and not making a decision which can benefit us. This will be highlighted by our next example. The next example is of lunar eclipse. For centuries, humans have been observing that the moon, from time to time, when it is the full moon night, happen to lose its brightness. Sometimes partially, and sometimes it would completely lose its brightness and a dark shadow would come over the moon. This is called lunar eclipse. For people living in this world centuries ago, this was an unpredictable event. They knew that it is going to happen on a night when moon is supposed to be full, but they did not know why it happened, and they could not precisely predict why, when and why it's going to happen. With the advances in astronomy, please note, I did not say astrology, I said astronomy. So with advances in astronomy, humans were able to understand better way how the heavenly bodies, earth and moon, revolve around sun. They were able to measure their movements with precise instruments, telescopes, and they were able to create a model which allowed them to predict when the next lunar eclipse or solar eclipse is going to be. But unfortunately, particularly in our society, there are still people who have no idea that with the advancement of science, this event is no longer an unpredictable event, and they do superstitious things whenever there is a lunar or solar eclipse. If you go to this website, which is run by NASA, then you will see that by using that model, they have been able to predict all the lunar eclipses which did happen or which are going to happen over a 5,000 years period. From 2000 BC to 3000 AD, they have tabulated all the instances of lunar eclipse. Not only that, but they have also tabulated when the lunar eclipse will be partial and when it will be complete, and on what countries of the world this lunar eclipse will be visible. So we live in an unpredictable world. We cannot have precise knowledge of all the factors that are affecting things around us, but it is quite possible to gather as much knowledge as we can and then make decisions based on those knowledge that are going to be beneficial for us. But the question is, the unpredictable world that we live in, the unpredictability of this world is a bad thing or good thing? Can we live with this unpredictable nature of the world? Can we make some use of it? The answer is yes. this unpredictability is not a bad thing in every case. In certain instances, we can benefit from this uncertainty. There are certain things that are so unpredictable that we make use of them, particularly in games of chance. A very common example is the coin toss. A coin is usually tossed before a sporting event to decide which team is going to bat first or ball first, depending upon what the captain of the winning team is going to decide. Or in case of football, a coin toss is used to decide which team is going to start from which side of the ground. So what happens in a coin toss? You take a coin, you put it on your finger, put your thumb below the finger and give it a flip like this. And you don't catch it. Well, you can catch it, but usually you let it drop on a hard surface. The coin bounces off the hard surface, makes a few more flips, and then rests on the ground. The coin is a thin circular object, and it can come to a stop either this face coming up or this face coming up. It's not possible for the coin to come to a stop like this. So there are only two possibilities for this coin to come to a stop. These two possibilities are usually called head and tail. So one side of the coin is called head, the other is called tail. So before giving it a flip, even if I know which side is up, I cannot predict what will be the side facing up when the coin comes to rest. Neither can anybody else. So a coin toss is quite unpredictable event for everyone. And why is it so unpredictable? Before going there, let me show you something which is not a coin toss but a coin drop. So next time you are out there playing a friendly cricket match, propose to the captain of the other team that instead of coin toss, you are going to do coin drop in a certain way. And that way is like this. You take a coin, see what is on the top side, and then you hold the coin in your hand like this, give it a twist and let it drop on a soft surface. It can be a sand pit or palm of your hand, anything from which coin does not bounce off. So here it is. It's tail side up. If I give it a twist, it drops and tail side remains upward. If you propose that to the other captain of your team, he is going to have a lot of heated discussion with you, and you will see that you will have to resort back to the coin toss, because a coin drop like that is not unpredictable. The reason is you are taking all those forces which are making this event, the coin toss, unpredictable away. By observing the side before you drop it, and by giving it a twist, and by not allowing it to bounce off the surface on which it is going to drop, you are taking so many uncertainties away. And then it's no longer a fair coin toss. So what makes a coin toss so unpredictable is that when you place it on your finger and give a flip with your thumb, you cannot precisely control the amount of force that you are going to apply with your thumb. Sometimes you can apply maybe 10 Newton, sometimes you can apply 15 Newton. Even if you try to apply 10 Newton the next time, you cannot do that. Humans are not capable of precisely imparting a certain amount of force. So by trying to apply the same force that you applied before, you might be applying slightly less or slightly more force. Furthermore, if you apply a 10 Newton force here and you apply 10 Newton force here, then the distance it travels before it touches the ground is different. And it's quite possible that while it is traveling these two different distances and it is flipping, it may make unpredictable more or less number of flips. So a coin toss is quite unpredictable, and it is quite useful because then the two teams can leave the decision of who is going to bat first on the outcome of the coin toss. There are other useful unpredictable events that are used in games of chance, gambling, and in one instance the prize bond lottery. Of course, when Government of Pakistan, the Savings Directorate, when it holds the draw for a certain series of prize bond, it does not flip coins, it runs a software, a computer program which is called a random number generator, and this software picks a few hundred numbers out of a total of 1 million possible numbers representing all the prize bonds in a series, and those lucky numbers are the winners, and they get starting from 10 times and going all the way to 200 times their initial investment. So unpredictable events can be useful, and we can make use of them to come up with a fair and acceptable solution to a game of choice or any other such scenario. Let's look at another example of unpredictable events, and that is the travel time of moving objects. As I said, we live in a dynamic world. Things move, we go from one place to another, we go from one city to another. But while we are moving, can we precisely predict when we are going to reach a certain destination? In academic environments, sometimes we pose such problems of moving objects which we solve under very idealized conditions. Suppose an object starts from point A, increases its speed to point B, then remains at that speed and continues to travel till point C, and afterwards it decreases its speed and comes to a stop at point D. So in idealistic environment, it is possible to precisely find out the travel time between point B and point C, the 2 points between which the object is moving at a constant speed. Suppose if point B and point C are 20 meters apart and the object is moving at 2 meters per second, then it is quite elementary to find out that the travel time for that object will be just 10 seconds. And that is how we get it, by dividing 20 with 2. 20 being the distance between 2 points and 2 being the speed with which the object moves between 2 points. In real life, things are not so simple. Suppose you decide to go from Lahore to Islamabad, and you decide to use bus service, one of the many bus services that are available in Lahore near Lahore Fort, the Badami Bagh bus stand. What happens in those bus services is that the bus company puts a bus, advertises it that this is the bus going to Islamabad, and then they start issuing tickets, and the customers reach, buy a ticket, and the bus continues to get filled, and the bus only starts when it is completely full. So you have decided to use that bus service. Once you reach there and buy a ticket, can you precisely tell how long it will take for the bus to get completely filled before it leaves? You cannot, because there are so many unpredictable factors that are going to affect this thing. And those factors are the arrival of other passengers. Someone is starting from one locality of Lahore, another person is starting from another locality, they are moving through the traffic of Lahore, everybody is facing uncertain traffic situation, and they reach the bus terminal at unpredictable times. So it's not possible for you to predict how long will it take for the bus to completely get filled. Suppose the bus is full and it starts its journey. Can you precisely predict when it will reach Rawalpindi? You cannot. Because in real life, when a vehicle is moving from one place to to another place which is far away from the first place, there are so many things which cannot be predicted. The traffic condition on the road, the weather condition, the condition of the bus, and even the wind direction. If the wind is opposing the movement of the bus may not be able to travel as fast compared to if the wind was coming from the side or coming from the behind. You can have an intelligent guess that the bus will reach from Lahore to Islamabad in 4 to 5 hours, but you cannot precisely predict it. So it is important for you to predict your travel time, but it is also quite important for the bus company to predict in an intelligent manner many factors which are going to affect this transportation business. For example, they have to predict based on their knowledge of the past behavior of the arrival times of passengers. They have to make a decision how many buses they need to put in so that they can accommodate all the passengers from morning to the evening. They also have to predict how big a waiting lounge they have to provide for the customers who are waiting for the bus to get filled, if they provide a waiting lounge at all. Usually, when you buy a ticket, you either go and sit in the bus or you wait on the footpath. So, in a real life situation, there are so many factors that are affecting the things that are changing around us, and we cannot precisely predict the effects of those factors that are affecting the dynamic world around us. That makes the whole world around us very unpredictable, but we can use mathematical tools to analyze these unpredictable events and make intelligent decisions, such decisions that are going to be beneficial for you more of the time than not. So what kind of mathematical tools we use to analyze unpredictable events? The study of unpredictable event is called probability theory, and it heavily relies on set theory, and it also uses differential calculus. So we will start with our quick review of set theory. What is a set? A set is a collection of objects with some common property, a common characteristics. Please note that I have written a common characteristic in parentheses. It's not necessary for the objects that are being put together to form a set to definitely have a common characteristics, as we will see. So let's look at a few examples of real life sets. First example could be all the people who live in a particular sector of Islamabad, say F6, F5, G9. This is a set. They share these characteristics that they live in a certain geographical location. Moving on, another real life example of sets would be all the cities of Pakistan which have more than 1 million inhabitants, and Islamabad is one of them. Moving further, we can have an example of sets. The set of those countries which have 90% or more of its population Muslims. So those countries where majority of population is Muslim also form a set. And lastly, an example of a set is all the planets of our sun which have at least one moon. Our Earth is one of them, Jupiter and Saturn are of course one of them, and Venus is not in this set. So these were the real life examples of set. But in mathematics, we usually deal with sets of numbers. And here are commonly used sets that we are going to deal with in mathematical analysis of unpredictable. The most common set is set of natural numbers. It is usually denoted by n, and it has numbers 1, 2, 3, 4, 5, and on and on. It never ends. It is an infinite set, and it has these positive numbers starting from 1 and going all the way to infinity. The next set, which is a superset of this set of natural number, is called set of integers. It contains whole numbers in addition to containing 1, 2, 3, 4. It contains -1, -2, -3, -4 and 0. So set of integers is a superset of set of natural numbers, and set of natural numbers n is a subset of set of integers. I hope you know all these relationships of subsets and superset from your undergraduate studies of set theory. There is an interesting property of sets which is called closure. The closure is that if you take two elements of a set and combine them together under some arithmetic operator where the result is, if the result is still inside the set, we call that the set is closed under that operation. It's quite obvious to see that the set of natural numbers n is closed under the operations of addition and multiplication. That is, you take two numbers, two natural numbers, add them together or multiply them together, the result is again a natural number. It's not true for the case of subtraction. If you take two natural numbers and subtract one from the other, it's possible that the result is again natural number if you subtract the smaller one from the larger one. But if you try to subtract larger one from smaller one, the result is not a natural number, it's a negative number. So set of natural number is closed under addition and multiplication, and set of integers z is closed under addition, multiplication and subtraction, because you take two integers, positive or negative, add them together or subtract one from the other or multiply them together, the result is again an integer. What about the operation of division? If you take two integers and try to divide one with the other, with one careful restriction that you cannot divide by 0. So if you take two integers and divide one with the other, it's possible that the result is again an integer if the divider divides the upper number completely. But it's not a guaranteed thing. If you take a number, a divisor which is not completely divisible by the divider, then you get a fraction. For example, 1 by 2. You take 1 and you try to divide it by 2, you will not get a whole number. You will get a fraction, 1 by 2, a half. And this fraction is not in set of integers. So the next set that we usually work with is set of rational numbers. It is denoted by Q, and it is all possible fractions, all permissible fractions. You take any two integers and divide them, divide one with the other, and the result is a rational number. Once again, division by 0 is not allowed. Other than that, you take two integers, divide them, and you get a fraction. It's quite possible that the divider divides the upper number completely, you get a whole number. So the whole number is also part of rational numbers. So rational numbers are all integers, 0, and all fractions with finite denominator. If you know a little bit about number theory, you will know that these rational numbers are very densely packed on the number line. What is a number line? Number line is a straight line. On that we have 0, and after a certain gap we have 1 and 2 and 3, and on the other side we have -1, -2, -3. The distance between two consecutive integers is same. So it's a to the scale representation of magnitude and value of the numbers that we are dealing with. So integers occur with gaps, a unit size gaps, and in this gap there are a lot of rational numbers, a lot of fractions. Actually, if you take two integers, say consecutive ones, 3 and 4, and you add them together and divide by 2, that is, you take an average, the answer will be a fraction, and it will lie right in between the two integers that we used to find the average. Not only that, you take any two integers, not necessarily consecutive, and take the average, the result will be right in between the two integers we take. And you can extend that argument and say, if you take two fractions, two rational numbers, anywhere on the line, add them together, divide by 2, you will get a fraction, a new fraction which will be right in between the two fractions that we started with. So you have 1 by 2 and you have 1 by 3. Add them together, divide by 2, you will have a fraction right in between that number, 1 by 2 and 1 by 3. You can continue and take this number, this rational number, and find average of this number and this number, you will end up here. You do it again, you will end up here. This never ends. The rational numbers are so densely packed on number line that it's hard to imagine that if there are any gaps between them. But actually there are gaps. About 2000 years ago, maybe a little longer than that, Greeks discovered that it's not possible to represent all numbers as fractions. Before going that, let me tell you something, that the set Q, set of rational number, is closed for addition, multiplication, subtraction and division. So moving on to what Greeks discovered a long time ago, they discovered that it's not possible to represent all numbers as fractions. We were talking about operations of addition, multiplication, subtraction, addition. Let's talk about an operation which is square root. You clearly know the operation of square. You take a number, you want to find its square, you multiply that number with itself, you get a square. So 4 into 4 is 16, so 16 is square of 4. The opposite of square is square root. So if you start with 16, you take its square root, you will get 4. You want to find square root of 4, find a number which when multiplied with itself give you 4. Of course the answer is 2. What will be square root of 2? Square root of 2 will be a number when multiplied with itself will give you 2. This number, let's call square root 2, is larger than 1 and smaller than 2. It's somewhere between 1 and 2. But it is not possible to represent this number as a fraction. And Greek discovered this a long time ago. So, if you deal with fractions, the rational numbers, they densely pack the number line, but they still leave some gaps. And these gaps are called irrational numbers. So irrational numbers are the numbers that cannot be represented as fraction of two integers, a over b, where a and b are both integers and b cannot be equal to 0. So there are numbers which cannot be represented as a over b, and these are irrational numbers. I gave you an example, square root 2. There are many more irrational numbers. For example, square root 3, e, pi, log of e raised to power pi, and there are many other irrational numbers. You may think that the gaps that these rational numbers leave are very few, the numbers like square root 2, square root 3. Actually, there are more irrational numbers than there are rational numbers, and irrational numbers outnumber the rational numbers by a big margin. All these concepts are part of number theory, a wonderful subject, and if you want to know more about all these numbers and how they densely pack the number line, you should study a little bit about number theory. So we deal with numbers, integer numbers, natural numbers, rational numbers and irrational numbers. The last set of numbers that I'm going to discuss is set of real numbers. It contains all these kind of numbers, natural numbers, integers, fractions and irrational numbers. So you can say if you combine all irrational numbers and all rational numbers, you get your real numbers. So real numbers contain everything, and they are represented as a decimal number. And the decimal number is written in such a way that you choose a base b, and then you choose different place values. And the number is an infinite series, infinite sum of numbers, where these numbers are of the form the first placeholder divided by the base plus the second placeholder divided by the second power of base. So if base is 10 and your number choose to be 0.532, then 0.532 means that it is a real number written in decimal form, but actually it is a sum of three fractions: 5 over 10 plus 3 over 100 plus 2 over 1000. 5 over 10 raised to power 1 plus 3 divided by 10 raised to power 2 plus 2 divided by 10 raised to power 3. So you can continue to add higher powers of the base b, and you will get a decimal representation of number. So if this decimal representation ends at a certain place value, at a certain digit, and afterward it's all zeros, then you have a rational number. Because if you add a finite number of fractions of the form ai over b raised to power I, then you can combine all those fractions and your denominator will be a finite number. So if the decimal representation ends at a certain digit and afterward they are all zeros, you have a rational number. Not only that, if the decimal representation starts repeating a certain pattern after a certain digit, so you have a number, say 0.32, 52, 52, 52, 52, it continues on and on and on, you still have a rational number. So how do you recognize an irrational number if it is written in decimal form? The irrational number have an infinite decimal representation without any repetition. That is, an infinite decimal number, a sequence of numbers written as decimal representation of a number represents an irrational number. Let's talk about pi, the well-known irrational number. In high school mathematics books, it is written as 22 over 7. That is wrong. 22 over 7 is a rational number. It's a fraction. It's incorrect to write pi as 22 over 7. Sometimes people write it as 3.1415, 3.14159 or 3.1416. That is again wrong. You cannot stop at 3rd, 4th, 10th or 20th or 200th digit. Pi is an irrational number and its decimal representation never repeats and never ends. Well, there are people who are trying to prove their mental power, their ability to remember long sequence of numbers, and they remember this non-repetitive decimal representation of pi up to 2000 or even more decimal place. Irrational numbers are wonderful. Their decimal representation never repeats, and there are more of them than there are rational numbers. So the question is, how many there are? Of course, you know that the natural numbers are infinite. You start with 1, 2, 3 and go on and on. And you also know that the set of natural number is closed under multiplication. So you take any natural number and multiply with 2. 2 is another natural number. The result will be a natural number. So since that is a natural number, you can again multiply it with 2, and you will make a big jump and you will end up at another natural number. This never ends. You cannot completely cover all the natural numbers even if you make big but finite jumps. So it's obvious that there are infinitely many natural numbers. They start with 1, 2, 3, 4 and go on and on and on. There is no limit to that. The integers are positive and negative whole numbers and 0. It appears that in set of integers z, there are natural numbers 1, 2, 3, 4 all the way to infinity, and there are negative numbers, negative whole numbers -1, -2, -3. For every positive number, positive whole number, there is a corresponding negative whole number. So it appears that the set Z contains twice as many numbers as set N, the set of natural numbers. Actually, it's not correct. It's incorrect to say that set Z has twice as many numbers as set N, because set N is an infinite number. If it were a finite set, a finite number of elements, then we can say that another finite element with twice as many numbers will have twice as many numbers. But since set N is infinite, it never ends, and it is meaningless to talk about 2 times an infinite quantity and 3 times an infinite quantity. You cannot say that this set N has these many numbers and set Z has twice. So how do you find out the number of elements in a set? That is called cardinality of a set. So cardinality of a set is the size of the set, the number of elements in a set. For a finite set, the cardinality of set is actually the number of elements in that set. But for infinite set, you cannot have a certain number assigned to it, because there are infinitely many elements in the set. But there are different types of infinities. As we have seen, set N, the set of natural number, is an infinite set because it is closed under addition and multiplication. You can take any element in set N, multiply it with twice, you will move forward and you will get a new natural number. Multiply it with 2 again and you'll get a new natural number. You don't have to stop. You can continue, make bigger and bigger jumps and keep on going, but you will never end. You will never exhaust the set of natural numbers. There are infinitely many. So how do you compare an infinite set with another infinite set? That is through one-to-one correspondence. You say, okay, you take a friend and you say to your friend, take this set and I'll take this set. You keep on taking elements from your set and I'll keep on taking elements from my set under a certain meaningful rule. And if neither you nor I exhaust our sets, if you can continue for 300,000 years and I can continue for as long, and I will continue to match your new element with my element, then we have the same kind of infinite sets. So there are 2 kinds of infinities. There are finite sets, their cardinality is finite, the number of elements. For infinite sets, there are 2 types of infinite sets and there are 2 types of cardinalities. One type of infinite sets are called countably infinite sets. These sets are such that their elements can be counted, like 1, 2, 3, 4, 5, in a certain way. In other words, you can have all the elements in an infinite set and put a one-to-one correspondence between elements of those set and elements of n. That is exactly what counting means. You have those elements and assign 1 and 2 and 3 to those elements. So you are counting or putting one-to-one correspondence to that. So if you have a set and you can have a one-to-one correspondence of elements of those set with n, you have countably infinite set. Let's take the set Z, set of integers, and see if it is countably infinite or not. It's very easy to establish that set Z is countably infinite because there exists a nice one-to-one correspondence between elements of Z and elements of n. You take your set Z, here is your 0, positive numbers are to the right, negative numbers are to the left. Then this is how you count. This is 0 is your first element, 1 is your second, minus 1 is third, plus 2 is fourth, minus 2 is fifth. You keep on going like this and you never exhaust your counting, but you continue to cover all the elements of Z. So Z is countably infinite. What about Q, set of rational numbers? I told you it densely packs the number line. There are infinitely many fractions or rational numbers between 0 and 1, and actually there are infinitely many fractional numbers between any two fractional numbers. So does it make this set any way larger than the set of natural numbers? The answer is no. I'll not go into the proof of this. You can go and see a good book on number theory, and it will clearly show you that set of rational numbers is also countably infinite. What about R, the set of real numbers? It is not countably infinite. It has much more, many more elements than the fractions, the rational numbers. The set R is called uncountably infinite. So as we discussed, the fractional numbers leave gaps on number line, gaps like square root 2, pi, e, and the real numbers, they don't leave any gaps. So all these nice concepts about continuity of real line, the different kinds of infinite sets, that is countably infinite and uncountably infinite, they are the foundations of understanding mathematical analysis of probability theory. To recap what we have covered in this lecture, we have just tried to motivate ourselves that why we need to study probability theory. We have seen the importance of capturing of all available information to make intelligent decisions that benefit us. And we have covered some fundamental concepts of mathematics, particularly set theory and the continuity of real line. The set theory, the number theory, and how there are different types of infinite sets, countably infinite and uncountably infinite. In next lecture, we'll start with axiomatic probability theory, where we will try to fit a formal mathematical framework to unpredictable events, and then we will use that mathematical model to study those unpredictable events. And based on our mathematical analysis, we'll be able to make intelligent decisions about unpredictable events, decisions that are going to benefit us. Thank you.